To begin talking about continuations, I talk about API and functions that pass results via callbacks. So that's a style of programming which sometimes is called continuation passing, but I believe in industry it's called callbacks, not continuations. But it's the same thing. So it's a style of programming where each function takes a second argument up or an additional argument to any other arguments it takes. And this argument is a function that consumes the result of a computation. So whatever function you want to compute, whatever value you compute, you don't just return it. You call this function on that value. So that function is the callback. And an example of programming in this style is if you define functions like this that perform some computations, compute result values, but then call the callback on that result value. And these functions return unit. They don't return the result values. So it's the callback that gets the result. So I defined these functions just for testing in this style. And later we will see an example of a Java API that uses callbacks, which is more realistic. But this is just for simplicity. So a constant function does not make any computation. It just takes its x, and that's already the result. So then it just calls the callback on that result. So how would we use functions programmed in this style? Suppose we have a computation which is basically 10 times 4 plus 3. We'd start with 10, which is a constant, but the const function has a second argument, so we need to provide a callback for it. We provide a callback like this, so now we are inside the callback. We have the previous result, which is going to be 10. We call the multiply, and again need to provide a callback. Now inside the second callback, we have this result, which is going to be 40. We provide this computation and another callback. Now, inside the last callback, somehow we need to store the result. Since we're not going to return anything as a value, we need to store this result somewhere as a side effect. And so we must use a variable, a mutable value, and then we store in that mutable value. So then, after you run this mutable value will be equal to 43. So that is an example of programming in the callback style. Now, in this example, this is completely pointless. This is just for simplicity. Where it is probably not pointless is if the computations are done asynchronously. So then this callback is scheduled, but not called immediately. So here's an example of exactly the same computation, but I just put all the callbacks in a separate thread. So I just put all the same computation, except the calling of the callback occurs on a different thread. So it occurs asynchronously. So what happens here is that this function returns immediately with a unit value, but it has scheduled to do this computation and to call the callback when it's done. So that is the typical situation where you have an API with callbacks. These callbacks aren't going to be called immediately. They're going to be called later. And so that's why you can't just return the value right away. The value will be returned later. The callback is scheduled to be called. And so that's fast. So that's the usual reason people have these APIs with callbacks. So I just reproduce exactly the same computation getting 43. Except that now we need to wait a little after we call this. Because this is not going to be calling on a separate thread each time. So unfortunately, you see, this is a very hard to use API because there's no way for us to know how long to wait. So we are scheduling all these computations, but we have no handle on the result, when the result is going to be available. So this is not very, very good. So essentially, this is the list of problems that we get with callback APIs. So the first problem is that we have no idea when things are finished. In order to get things finished, either you put everything in the innermost callback. So after everything is done, you will be called in that callback. But that means all your code now needs to be in that callback. All the code that comes next after this computation, it has to be all in the innermost callback. Otherwise, you have no idea. I mean, this is a very bad coding practice to have a random wait in order to let it run. That's extremely unreliable. Another problem is that you get code that is deeply nested. So it's not easy to get values from one place to another. And if you need to do that, then you need to do a lot of refactoring. So imagine there's some value that I want to use here, and this value is in some other place, in some other callback. Then I'm now starting to write spaghetti code, mutating some variables and whatever. It's a very bad idea. So it's hard to pass values from one place to another, because all of this is deeply nested callbacks. Another problem is that these callbacks are not composable. So if I have one such computation, I cannot easily combine it. So I have this, for example. I cannot easily combine it with another such computation, because to combine it, I would have to put code into the innermost callback. But the code is already written. So I have to do something, again, with mutable values, or it's hard. So once I start passing callbacks around, it's very quickly becoming almost impossible to understand what the program is doing. And that is called, usually in the industry, callback hell, which means that you have a lot of calls to some callbacks, and you have no idea when they're called and who calls whom. So how do we solve this problem? So the main idea of solving this problem is to make callbacks composable. So what does it mean, composable? So let me just reproduce the simplest fake API that I have here, which is a callback-based API. And let's understand what it would mean for it to become composable. So for example, I want to take this, then I want to have this function that multiplies, and somehow I want to compose these two. What would that mean that I compose them? So let's look at the types of these values. So C10 is the constant of 10. Actually is a partially applied function, so it has this argument, but it doesn't yet have this argument. And so it's a value of type, a function from this to this. So that's the type of C10. So if you look at this type carefully, you see it's a function that consumes a callback. So it will register a callback, but it will then return unit. And so that's what it will do. So, okay, well, for brevity, let's define a type, which is RC, for functions that register callbacks. And they're just going to be like this, okay? So we define this type. Now, step one of this computation is going to be this. So we want to now combine C10 and step 1. Well, step 1 is this function that takes x and multiplies by 4, right? So what is the type of this function? It's like this. So this is our second step. Now, what if we could write something like this? We compose C10 and step 1 using some operation. Let's try to understand how we would define such an operation. So what we want is that the result of this operation should be again of the same type, of type RC of int. And then we can compose further. So basically, the idea of this operation is that it will take the previous value of type RC of something. It will take a step, which is taking this computed value and doing something with it. And the operation that combines should know that what we mean by this function is that whatever the previous step computes needs to be put as this x. So somehow we need to put that into the callback of the previous step. And that x needs to be used. So for example, for C10, that should be 10. So the combine operation should somehow understand that what we want is that the 10 here must become x. And then this should be mul4 of 10, really, when we combine. That's what this combine operation needs to understand somehow. So that's our goal, all right? We will see very quickly how to implement that. And the reason is functional programming magic. And we'll see how that works. So let's see step 2 now. Step 2 is adding 3, same thing. So now we want to write this, and then we will get C43. So the result should be the same as if we had constant 43. That's the idea. And then we will be able to write C10 combined with step 1, combined with step 2, just like that. It will be very easy to combine. So what is required to be able to implement this operation? Just look at the type signature of this operation. It takes RC of int, it takes a function from int to RC of int, and it returns another RC of int. So let's implement this operation as syntax. I'm just doing an implicit class here for syntax extension. It's basically putting another function on this as syntax. But let's do this with type parameters. So I have RC of A, I have A to RC of B, and I return RC of B. So that's the function we want to implement. That's the type signature, in any case, that we want to implement. If we implement this type signature, that's how we should implement it. Let's think about it. So this function should return RC of B. So RC of B is a function that takes a callback of type B to unit. So let's start writing code like this. We take this callback as an argument, and we need to return unit. Well, we will return unit. That's very easy. Just return unit. But what shall we do? Well, first of all, we need to implement this idea that the result of the previous computation needs to be put as x into the function. Now, the only way we can do that is if we call that RC, which is the previous computation, on a callback. That's the only way that we can get the value out of it. So the value A of type A, or I called it x before, is the argument of the callback that we're passing to RC. So that's the only way we can do it. So RC, let me just remind you what RC is. RC of A is A to unit to unit. So RC is a computation that will have its value, but it won't give you that value unless you give it a callback. So you need to register that callback with it. So we supply a callback. This is going to be our callback. it will take the value a, and now we have it. So now we can call f of a as we wanted. The result of f of a is an RC of b, which we can call on the callback provided. So then we write this code, f of a on cb. And that's the code. So we implement, therefore, exactly what we wanted. We implemented the idea that this operation at, it will take this function and understand that the argument of this function is supposed to be bound to the result of this previous operation. And that's how we do it. We pass it as a callback. Now we can write it like this. We're done. So now we have made them composable. It's very easy now to compose. To test this, let's define a function that extracts this value. So we put a var and so on. But this is just for testing. In real life, there will be some side effects in these callbacks, so we don't need to extract the value usually. But for testing, let's extract the value. Now, it works. Now, the type signature of this operation is very similar to that of a flat map. It's a type constructor of A, and then A to type constructor of B, and then it's returning a type constructor of B. And also, we have a function that has a type signature of pure, because we have this const, which had this type signature. And if we just generalize to the type parameter A instead of int, it's going to be the same code. And so that's the type signature of pure. So we have a type constructor for which we have a function with type signatures of flat map and pure. That's a monad. So this is the continuation monad. So we have found, so this is the code for pure. Just call the callback right away on this value. We can now, I'm just doing syntax for map and flat map here, so that I have, see, RC is a type, it's not a class. I defined RC as a type. So I don't have class here. I just define this as a syntax for this type. I'm done. And now you can use the same code with a for yield syntax. In a for yield block where we just write functions like this. And now this computation looks more straightforward. You take X from the first computation, then you put it in the second one, you get Y, you put it in the third one, you get Z. And this is just for syntax reasons, the way I defined it. And again, it works. So what is the result of this? We have now easy access to the innermost callback in some sense. So this diagram, I wanted to illustrate how that works. Why is it that we have, oops, I think it's not very beautiful. Anyway. So imagine again how this operation works. This operation, it takes this value and this function, and it returns this value. But how it works, first of all, it gets this A out of here and calls this function on it. And then it substitutes this callback in here, because that was our code, right? You see this flat map. We take the A and we call f on it. So we call this function f on that A. We get this, and then we substitute into it the callback. So because of this, we have access to this innermost callback. This is it. This is the innermost callback in this little computation. And we have easy access to it because we expose it here as the argument of what we return. We return a value of this type, which allows us to very easily substitute something into this, which is going to be put into the innermost callback. So in this way, this trick gives us immediate access, very easy and immediate access to the innermost callback of this nested callback thing. So that's why it's so easy to compose. So you take this, you can very easily continue. So you know, result 2 has the same type. So I could easily write code like val result 3 equals 4, and then x going to result 2, y, and so on. You know, add 3 of x. You can just continue with no problem whatsoever, because you have such easy access to this innermost callback, which you don't have otherwise. You don't have it. And that's what makes it composable. So now let me show you a more realistic example where I use Java NIO API to read and write files. And this API uses callbacks. So that's an example of this API that would be very hard to use if you were using it as they intended. So they wanted you to have the hard time, basically. They made this callback API. And this is how it works. So first of all, you get this file channel by opening a file. You get a file channel, which is a special value of this type. Then you have to allocate a buffer for it. And then you call the read operation on the file channel, which pass in the buffer. And then you don't get the result back from this function. You need to pass in a callback. Now, the callbacks in Java, of course, are classes, which have methods in them that you have to override. And so you have to pass in this completion handler, which is basically a glorified callback. It has failed, completed, and that's it. Yeah, failed and completed. So you have to override 2 functions. So basically, you give 2 callbacks. One will be called when it's failed, and another will be called when it's completed. So let's ignore the failures for now, and let's just look at the happy path where everything works. So with completed, what do? You have a function. This is the callback, which is going to give you some integer, which is the number of bytes read. And that's attachment. We don't use it for now. But where's the data? Well, the data was put into this buffer. It's a mutable structure. So at this point, the buffer is not empty. So in this callback, you can put code that uses the buffer. So for example, you rewind the buffer, whatever, close the file channel, and then let's copy this to another file. So now we have to be inside this callback in order to copy to another file. Otherwise, we have no idea when the buffer is ready. Okay, so we're inside this callback. We open another file channel. Now we write this buffer to this file channel. We pass a new completion handler, inside which we again have to put a failed and completed. So now we're inside the second callback, which gives you a result, tells you how many bytes it wrote. You have to close this. And now we open a third file channel. We read. So what we want is to check that the result is correct. So we copy the file. We want to read that new file now and check that the text in it is the same. That's what this test does. So how many lines of code have I written so far just to do that? It's like, yeah, it's like already 20 lines of code at least. Okay, so now I'm in the second callback, and now I'm in the third callback. Result 3 is again integer. I again rewind. Now I can examine the second buffer. Only in this innermost callback, I can examine the second buffer. I can check that it is the same data as the first buffer. And this is my test. So is identical is going to be printed. This is my side effect. Now, we'd like to return this, but we're in a deeply nested callback. So, okay, well, somebody give us another callback right here, and we'll call it. That's how this programming goes. You just keep passing callbacks around, because otherwise you have no way of accessing this deeply nested code. So this report result, I commented it out because I did not implement it like this, but you would have to accept another callback in order to report anything out of this. So, all right, so now let's do the same code using the continuation monad, which I just define as this cont. Cont is a little more general than a unit. Cont is defined like this with a type parameter r. But for now, we're going to use unit instead of r. And so if you look at this, it's just a case class that has this thing inside, and it has methods. It has, well, it's in a cats library, the functor and the monad instances. I'm not going to cover that, but this is basically the same code that we were writing up there. The same code for flat map that we were writing up there. It's just more general because you need this type parameter. So right now, here's what we do. The first thing we need to do in order to use this monad is to convert these Java APIs into values of this monad. So remember, we started with these functions, these add, mul, and so on, but we need to convert them into monad values, into values of type RC of something. And that's how we do it here. This is conversion going on. But Java APIs aren't written like that. So we need to explicitly define the NIO read of this type. And we're free to define types here, right? It's just NIO monad is a type constructor. So it's going to be A to unit, basically. So we need to encapsulate all that code with this callback and so on by providing the result that we want. So a continuation takes a callback and calls that callback inside somewhere. So we just put the same code in this new interface so that instead of a function, NIO read with arguments that returns nothing, we have this value of this type. And that's just a convenience. So we put that code here. NIO write, similarly, we need to put it into the monad type, which is the same code as we had before, but it's just packaged now in smaller chunks. And then we write code. Okay, here's the code. Open the file channel, and then we start a for yield. First, we read this. Okay, now this is now one line of code to read a file. And we get at the same time the integer number and the buffer as results. Now we get them as values. Much easier to reason about such a thing. We have values now. We open another channel using this value we write to that channel. That returns nothing. We don't care what it returns. And then we open a third channel and we read. And we get this result. And now we return this test, that result 1a is equal to result 3a, and so on. The strings are equal. So now we have a for yield block that is much easier to write because it looks like we're just computing. We read the file, this is the result. Create a channel, read and write to that, this is the result. Create a channel, read from that, this is the result. Much easier to write this code and to work with it. If you want to refactor it, it's easy. All the values are in here. So as if you're working with values. Now let's run it. In order to run this, we need to provide a callback. So the run is what is inside the case class, and it takes a callback. Let's just print the results. So let me just run this code, actually. And we'll see that it works. I did check, but let me just run it. So yeah, right. Status is true. And so it did everything, checked that the new file is the same text as the old file, and printed the result. So there are still some deficiencies here. One deficiency is that we can't wait for operations to finish. And so this works only for synchronous operations. Indeed, this Java API I'm talking about is not synchronous. It could be used in an asynchronous way, but we haven't done it. We are using it as if it's synchronous. And also, we can't catch exceptions right now. We don't have code that can catch exceptions. So this can be done if we, instead of doing A to unit, if we do A to R, like this. Because then the callbacks can return values, and these values can be examined, and they could carry error information, or they could carry other information. For example, a handle on some thread that you can check, or something like this. So the way it works is that you need to now use this A to R type in the way that registers a callback, but then returns a value. And this value could also carry some interesting information. So here's an example where I have computations that cost money. And the cost is returned as this extra information. But other than that, I have the same computations as before. So how would that work? What I want is that when the callback is run, it returns a double value, which is how much it cost. And now I can add more cost to it. So my cost is the cost of whatever the next people did, and then my own cost. So that's the idea. I want to have computations that do the same as before, 10 times 4, and so on. But now I want to keep track of costs for each computation. And that is automatic. If I use this data type, this continuation monad with a non-trivial result type. So here's how it looks now. I define add3 that has cost 10. So addition costs 10, multiplication costs 50. And look at this code now. It's still very easy to read and to write. But now it does two computations. First, it does the computation that I want, 10 times 4 plus 3. But then also, well, let me just move this over here. Let's do it over here because it's probably easier to understand. So what happens here is that all these callbacks are called, but when the result values are obtained, then there is this addition operation happening. So each of these computations will give you the result and also add up the costs at the same time. So there is well, this will happen on the way back after the callbacks are returned. So that means we have kind of one computation that goes into the forward direction into the nested callbacks. And when the last callback is called, it returns its cost. And we unwind it back, adding all the costs on the way back. So that's how this computation runs. And that's the result. I'm just testing it, that it's 43 with cost 60. So in the previous Scala group session, we looked at what I call the transaction monad, which was of this type. So it's a continuation that returned future. And this future encapsulated errors, and we could handle them. So on the way forward, we perform computation. On the way back, we can handle errors. And that was used to roll back the transaction in terms of errors, in case of errors. Anyway, this is just an example of how else you could use the continuation monad. Futures are similar to continuation monad. They are asynchronous. They are, well, you can chain them easily. So this is a bit more complex to use a future on top of a continuation monad, but that was what we did in the previous session. So I'm not going to talk much about it. So let me just summarize what we have done. So first of all, we know how to convert a callback API into a composable code. So code that will look like this. So if you have a callback API, you should do that, and you should not write callbacks yourself. You should hide all that, and make the code look like it's just composable computations. Because it's a bad idea to use callbacks. It makes code very complicated and hard to refactor, hard to use. Because you have to, the main problem is that you have to put code into the innermost callback. And that's impossible, because the code is already written. Somebody gives you this callback function. It's already written what was the callback. So you have to expose these callback arguments all the time and put them in, pass callbacks around. The code becomes very complex, and that's callback hell. So avoid that. Implement an adapter that converts the callback API into a monadic DSL. So this is basically the monadic DSL for callbacks. It can be also combined with future. So this is actually too complicated for an API that needs to be just combined to future. It's directly possible to combine to convert callbacks into futures. You just need to take a promise and adapt your API to futures. So if you have callbacks API that are asynchronous, then it's actually better to convert them directly to futures. This I don't believe this is necessary. So what I discussed in the previous session was actually too complicated. Could have been simplified, but it's okay. It's still the same idea. If you have a synchronous API with callbacks, convert it to continuations. If you have asynchronous API with callbacks, convert it to futures. Anyway, you will get a monadic DSL out. So let me just summarize what you get out of a monadic DSL. You have some type constructor, f, let's say, of some kind, which you will have to define. And your computations become programs of, that is, values of this type. And you combine them using flat map. So this is the basic building block for combining computations. So once you have defined what that type constructor is, you can derive this implementation and combine very easily different building blocks into a larger program and add more and get a larger program until you have the final program. The final program needs to be run. So this is the kind of function, or interpreted, if you wish. So this cost is a value that doesn't actually do anything. So you see, if you do this, nothing has been done yet. You have defined the functions that will be called, but you haven't called them. So this is the typical feature of a monadic DSL. You will write values that are programs, but these programs don't yet do anything. They have to be run or interpreted. So the function that runs them or interprets them has to be written. And then it will do something like this, maybe quite difficult, but it will be just written once, and then you would run it. So what is the cost of doing this? Well, first of all your computations now need to be lifted into the monad type, which is what I did here with this with this NIO API. So before I could use it, I had to define these two functions, NIO read and NIO write. I had to define them. So these functions basically lift my read and write operations into this type, NIO monad of something. Here is NIO monad of something. So that's a cost. You have to do it. You have to lift all of your computations into the monadic type, which means writing. So this is basically the adapter that you have to write, adapting the API into the monadic DSL. Second thing you have to do is you have to write the interpreter or runner that will run at the end of your computation. So that's the cost. So there's additional code to define this type, to define adapters that lift your API into that type, and to define the runner or interpreter for programs of this type to actually do something. Because those values are not going to be, they're going to be just values. They're going to be descriptions of things. They're not going to be actual running code. They have to be still run. The benefits, however, is that these values can be stored or composed at will before running them. So you can much more easily design your program. You can put them into an array if you want. They're just values. You just store them. And when you're ready, and when you know how and to run them, then you run them. So that could be a big advantage. And also, you could provide different interpreters or different runners for different purposes. You could provide a testing interpreter. You could provide an analyzer. You could guarantee that certain operations are not called or something. By running it through an interpreter, it doesn't do anything except gives you an error when some operation is there. It's very easy to do, and that gives you value, maybe in some cases. So that's all I had for today. And please, any questions?
Do you mention at the beginning of using futures for composing asynchronous operations? Could you use synchronous?
That's why that's why futures were made in the first place, so that we have a placeholder for the result. And so I'm not an expert with futures, but where's the contrast? Why would we take this continuation monad as opposed to just using futures?
So, right. So futures actually repeat quite a lot of the value of continuation monads. And actually, they give you more value because they catch exceptions. And so you can easily catch errors and handle them. However, futures are not values that can be stored and composed at will. Because unfortunately, well, this is really a design error in the Scala library, that futures, when you create them, already start running. Right. So that is a problem. In other words, future is not a description of a computation.
Yeah.
It is a representation, as a handle on some thread that's already running.
Got it.
So you already have a finger on it. And whether you want it or not, it's already running. So it does not have the right semantics of a purely descriptive language that you can just combine. And then, so for example, what you cannot, there's cost for this. There's also a value. The value is it's easier, right? You just have this feature, it's already running. It's easier.
There's no interpret.
There's no interpret, right. There's no separate step to run it, right? But there is a cost of this, and the cost is substantial in some applications. The cost is that first of all, you cannot make a future without providing some thread pool. So whoever makes this API needs to know where it will be scheduled. You cannot separate these concerns. You cannot have a logic that just tells you how to organize the computation, and then somebody else will later decide which thread pool to run it on.
Using features.
Yeah.
Here you can.
Here you can.
Because you provide the
Here you
thread
can.
that interprets.
Because you separately assemble your program, compose your program from parts, and nothing is running yet. You're just composing it from parts. And when you're done, you decide how to schedule it, run it, or whatever. Futures don't allow you that. They're not lazy. They are they mix these two concerns. And another result of the same is that the performance of futures cannot be optimized very well because they are already scheduled. So imagine I'm scheduling a future, and then I want to do a flat map on it, right? Now, flat map on a future means that when this first future is done, I call that function and I schedule a second future. Now, this scheduling cannot be done on the same thread as the first one. First of all, the first one is already running, and it might actually be already finished. And while you're still doing your flat map, right? You're scheduling the second callback, so to speak, but the first one is probably already done, or maybe not, we don't know. You have to provide another thread pool to do that. You cannot just, so you're confusing these concerns, and that's the cost. So for example, what you can do if you didn't have this confusion of design is that first you do all these maps and flat maps. You have a chain of futures which aren't running, which are just there. Then you can go over it and optimize, and make sure that you don't have some unnecessary maps or something. And then you have maybe a different DSL program. You can do that. And then you can run it. So when you run it, you can say, oh, I want to run it on a thread pool over here with such priority and so on. Somebody else can decide it, and somebody else still could optimize it. And it's completely impossible with futures. Futures don't have the greatest performance because they have to be like this. And so, so that's the main difference. However, all that said, for most applications, standard Scala futures are a good fit. I would not actually use the continuation monad without a very good reason. Right now, I gave you some examples, and in all these examples, I could just have thrown out the continuation monad, put in the future instead. It has a very similar property. And if I don't care about this confusion of concerns, that I have to provide threading information every time when I do any flat map, it's inconvenient, and it's wrong. It's not the right place to do it. But if that's okay, if that's not a problem, then it's actually easier to do that. It's easier to use futures than the continuation monad. It's easier to reason about them. Although, well, continuation monad is really very similar to a future, except that it's synchronous. And so it's very similar. So reasoning about them could be easier. And if this confusion of concerns is not a problem, then use a future. Actually, modern Scala libraries like CATS and Scala Z, they have new replacements for futures, which are called tasks or effects or something like that. And they solve this problem of confusion.